Okay, so now we're going to look at the second option, which happens to be the limit comparison test. So a sub n has to be bigger than 0, b sub n has to be bigger than 0. If that's true, then the limit as n approaches infinity of a sub n divided by b sub n is equal to L, where L is a finite positive number. So what we mean is that the series consists of only positive numbers. When we say greater than 0, so we can't have any negatives, which we'll talk about what we should do when we see negatives later. Um, if we get a finite positive number, then the series will either both converge or both diverge. So what we need to do is we need to choose a series that either converges or diverges, and when we divide those two functions, we need it to have a limit that exists and is positive. The nice thing here is we don't need to decide if the function is bigger or smaller than the other. We just need to make sure that we're not putting in any weird negatives into a spot to make it a negative value. Okay, so determine if the series converges or diverges. So the first thing that we're going to do is we need to choose what function that we want to compare this to. And then we need to make sure that we can find this as well. Just like the last time, one of the easiest ways to choose a function is to choose something that's similar enough, but is something that we can potentially kind of like move around to help us out. So when I look at this problem here, the square root of n divided by n squared plus 1, what I want to do is I'm going to pick the square root of n and I'm going to divide it by n squared. So the series that we want to compare it to is the same thing except for without the plus 1. So n equals 1 to infinity of square root of n over n squared. So the first thing that I want to do potentially is decide if we can say if this is a converging or diverging series. So what we're going to do is we're going to move this around. I have n, I can change the square root to n to a power. So we have n to the 1/2 power divided by n squared. We now have two variables that are the same raised to a power. So we can actually go ahead and divide these two things to subtract the exponents from each other. So we have 1/2 minus 2, which is going to give us the negative 3/2 power, but that also means I can write it as 1 over n to the 3/2 power. This is really nice because I have this form here, n to the power, and it's in the denominator. That means that it is a p series. P is equal to 3/2. 3/2 is bigger than 1, which means that this converges. So we have now decided that this function converges. So what we need to do now is look at the limit. If it gives us a positive finite number, then we know that our original series converges. So now we are going to be doing some division. So the limit as n approaches infinity of, it doesn't necessarily matter which one's which. We should be able to divide either or and get a value. I'm going to probably stick with having our original function on top and dividing it by the one we chose. So we are going to start with the square root of n divided by n squared plus 1. And we are dividing that by 1 over n to the 3/2. And I could change it to what I originally had, but I don't necessarily have to. Sometimes it's easier, sometimes it's not. Okay, so the first thing that I'm going to do is I'm going to go ahead and rewrite this as the multiplication of two fractions. So the multiplication of the reciprocal versus having division. So I have the square root of n, or n to the 1/2 power, divided by n squared plus 1. And we are going to multiply it by the reciprocal of 1 over n to the 3/2, so n to the 3/2 over 1. We have two fractions, so we're going to multiply straight across. So we have n squared plus 1 in the denominator. We have n to the first times n to the 3/2. When we multiply things like this, we are going to add them together. So we have n 1/2 plus 3/2 happens to be 4/2, or 2. So I have n squared over n squared plus 1. This is a Eats DC case because our exponents are the same, so the degrees of the top and bottom are the same. So we are going to divide the coefficients. Our coefficients on both the top and bottom are 1, so 1 divided by 1 is 1. 1 happens to be a positive finite number. So we already decided that our series that we chose converges. So what that means is the summation from n equals 1 to infinity of the square root of n divided by n squared plus 1 converges by the limit comparison test.